Thanks for coming, everybody. We can get started because we have a full session probably. I'm going to be talking about Delta Lake meets DuckDB via the Delta kernel. And what that really means is I'm going to tell you a little bit about what the Delta kernel project is and some of the things we've been doing in Rust to build the Rust version of that. And then about halfway through, or a little bit more than halfway through, I'll be handing over to Hannes Mureisen, who is going to speak about the DuckDB integration. You may have seen him at the keynote this morning. Cool. So a little bit of an outline. I'll just talk a little bit about why we want to build a Delta kernel. You might have heard some of this already. It's, we're in the last day of the summit. We've been talking about it a lot, but I'll just try to go over it quickly. I'll give you a little bit of an update about, then I'll tell you a little bit about what the Delta kernel is, a little bit of an update of where we are in the project. I'll talk a little bit about some of the challenges that we faced in building this in Rust, and then we'll hand over to talk about the DuckDB integration. So some of the motivation, we have this amazing, massive ecosystem of people who want to read Delta. Lots and lots of different connectors. I'm not even going to bother trying to read them all. You probably can't even see the logos, but those are all real things. And all of them at the sort of core in the middle want to just be able to read Delta. They need to implement this Delta protocol. And the thing about Delta is it's got a lot of stuff in it, right? Like Delta is an innovative protocol. We want to be able to have it move quickly. And it's got all these cool features. Last year in Delta 3.0, we added things like deletion vectors, row IDs, all these kinds of things. And all of these are in the protocol. If you want to understand them and use them, your connector has to implement that. Moving into Delta 4.0, and in the future, we're adding tons of cool new features, things like variant type, things like that, which as each of these things gets added, connectors need to be able to support this. And so coming back to this big ecosystem of connectors, what ends up happening is that you suffer from fragmentation in this ecosystem, right? Some connectors support deletion vectors, but not variant type. Some connectors support variant type, but not deletion vectors. And you've multiplied this by all of these connectors and all these features. It means that you don't get to really use the cool features of Delta when you want to, because some of your people are using this connector and it doesn't support deletion vectors, and other people are using this other connector and it doesn't support variant type. It slows down adoption. And so what we really want to do is replace, I don't know if you noticed that the little middle changed there, but we want to replace just the Delta protocol in the middle with the Delta kernel. And all of these, the goal is to have all of these things be using the Delta kernel. So the goal then of what we're trying to do in the Delta kernel is abstract away the details of the core sort of protocol details, and let developers who are building a connector and engine just focus on doing really good integration with the Delta kernel and not worry about, how does the Delta kernel, or how does the Delta protocol work? What are the different features? And then once they've done the work of adding this integration, they can easily stay up to date with the new features, because we don't want the APIs of the kernel to change too significantly, hopefully very little. But once you update the kernel, it just understands more, and you can use the new, latest and greatest features of Delta. So how do we want to do this? What is Delta kernel? So Delta kernel is a library. Well, not that kind of library, more like a software kind of library. This is what you typically think of when you think about a software library, right? Like I would just take some code, the Delta kernel, plug it into my engine or connector underneath, and when I need to read some Delta, I say, hey, library, please do this work for me. It goes and does some work, it gives it back to you. If that's all that Delta kernel was, it wouldn't really be worth me standing up here talking to you, right? It'd be like coming up here and announcing a new CSV reader or something. Like, that's not that interesting or exciting. What's actually hard about this? Well, one thing is we want to support all different languages. This is not that hard. We cheated a little bit. We're building 2 Delta kernels right now, one in Java and one in Rust, mostly because people who are in the JVM ecosystem don't love having to do native stuff, and people who are like fast native connectors really don't love having to bring in the JVM. So we just said, okay, let's not try to fix that battle. We'll tackle VI and Emacs first, maybe. And then, so we'll build two, one for native and one for non-native. The other thing that's hard, and I think this is one maybe that's a bit more interesting, is really how do we provide the right level of APIs? So the problem that you run into is if you provide high-level APIs, which is kind of like what that first picture I showed of a library is, it can end up being too slow. Engines might care a lot about exactly what data format they read things in. They might care exactly how they manage their memory. They probably do really nifty optimizations around how they multi-thread, things like that. If it's just a library that is very high level, we're going to blow all of that out of the water. Nobody's going to want to use it. They're just going to have to implement them themselves. On the other hand, if we go really low level and we just provide basically some abstractions over the Delta log, that's also not good because now every new feature requires that you really understand all the details there. And so what we're really trying to do is kind of hit this Goldilocks zone, which is APIs that are not too high and not too low. And that's a challenge. I'm going to talk a little bit about sort of how we do that. And if we can hit that, the goal is really provide the very best performance for every engine and let engines use the existing features, right? Like people who build engines have already done a lot of really hard work. For example, the DuckDB guys have implemented a really nifty, multi-threaded, super fancy Parquet reader. We don't want to therefore go build a Parquet reader for them. They don't need that. They've got a much better Parquet reader for DuckDB than we will ever be able to build. So let's let them use that in a pluggable way. So if you remember this picture, that's wrong. That's not what we're doing. It looks a little bit more like this. So sometimes we call this a U-shape architecture. Sometimes we turn it vertically and call it a C-shape architecture. I'm not sure which one we're going to settle on, but we kind of slot, the idea is that we slot the Delta kernel into the middle of the connector. And to do that, we have to sort of provide two different classes of APIs. So there's these table APIs, which are what you might expect from a normal library. It's things like, hey, I have a Delta table that I want to read, maybe with some predicates or something like that. And that goes into the Delta kernel. You call that as the connector. And then the kernel says, OK, cool, you've asked me to do some work. In order to do that, I am going to turn around and call right back into the engine, into these engine APIs. And what are these? Oops, we skipped a slide. What are these engine APIs? They're things like read some JSON, read some Parquet for me, evaluate an expression. And importantly, we are trying not to impose too much in terms of requirements on the kind of data that comes back from this. And I'll talk a little bit more in detail about that in a little bit, but we want to let the engine do that just kind of in the normal way, which is how they would normally do it if they were implementing this without the Delta kernel. Just read some JSON in your native format. And when we think about when you want to integrate the Delta connector, the Delta kernel, so if you're an engine developer or a connector developer wondering if you can use this, this is where the bulk of the work is going to be, right? Like calling the table APIs, that's easy. There's only a few of them. You just call them. But providing this engine implementation, that's going to be where you spend the majority of your time and have to do some actual work. Once you've done it, you get the free upgrades, but that's where a lot of the hard work is. But the good news is, why does it keep doing two? The good news is we've done a lot of that hard work for you if you speak Apache Arrow or if you can speak Apache Arrow. So we have a default engine implementation that gives you all of those APIs implemented already. And we'll give you back data in Arrow. I don't know if people know Arrow. It's just a very cool language-independent format for storing data. So it defines the in-memory representation. Lots of different engines can speak it and you can do it with zero copy, right? So I've read some data, it's in Arrow format. If I give it to you, you understand that format. You can potentially use it transparently. Cool, so then you kind of get to go back to this picture, right? Which is easy. This is like your normal library picture, but the Delta kernel just has a little bit of Arrow in it now. So that's what the Delta kernel is. And I'll just tell you a little bit now about sort of where we are. We recently released 0.1, actually 0.11 now, which was a culmination of hundreds of PRs. We have 14 different contributors at this point. At least 5 of those are non-Databricks people. So we're really trying to build it as a community project. We're really trying to make sure that we talk with connector developers and engine developers. is evidenced by the fact that we're going to have Hannes coming up and talking from the DuckDB perspective. Like, we want to make sure that we're not going away and building this thing and then saying, hey, it's here, and then have everybody be like, this isn't really what we wanted. We want to make sure that we're building things that people actually want to use. Where are we right now? So for those of you who know about Delta RS, the very cool Rust implementation of reading and writing Delta. They've started to take Delta kernel as a dependency. People are involved in the project, and they are just sort of dipping their toes in at this point, but are planning to do further migrations and have the kernel be at the core of Delta RS. And then DuckDB, right? We've released an extension there. People can go, you can go play with that. If you go into your DuckDB and type load Delta, you can query tables. And there's also the catalog integration that we announced this morning. So that's where we're at. Some of the major things that were in this release. So as I mentioned, we have this engine data API. This is an important piece that talks about how does the engine manage to read some data in its format and then still let the kernel poke at it in the ways that it needs to. We did a bunch of work to try to get as safe as possible an FFI interface. I don't know how many people here are familiar with FFI and sort of the grungy details of Rust and C and all that kind of stuff, but at a high level, Rust tries to be very safe. It tracks what's happening with all of your data. It's really just to prevent you from having things like seg faults and data races. But it also allows you to export an interface that can be called and call out to C. And once you cross that line, it's kind of like all bets are off, right? Because in C world, there's no compiler that's helping you. So any magic crazy things can happen, and Rust can't guarantee anything. So it's not possible to create a fully safe FFI interface, hence the quotes, but we've done a lot of hard thinking about how to make it as safe as possible. There's scan splitting here, which is basically, connectors. When you want to scan Delta, you might have to read a whole bunch of different files. You don't want to do that necessarily all in one place. You may have a very fancy multi-threaded Parquet reader and want to farm out all that reading to lots of different people, lots of different threads. You may be a fully distributed engine and need to send that over the wire to lots of different workers, so that's implemented. And we have data skipping via expressions. So if you pass down that your query is looking for value greater than 3, we can tell some Parquet files that are involved in this table don't include any data that might match that, so we won't read those files. We won't tell you to read those files. We support, for those of you who know what these features mean, just a quick rundown of the things that we actually support. Deletion vectors are supported. Partition columns are supported. Complex types like structs, lists, maps, nested, everything. We support data skipping, like I mentioned, via expressions, column mapping, which is like column renaming. And later this year, write support will be coming. It's on the roadmap as soon as we get time to work on it. So we should hopefully have that in not too long. Where can you find it? We've open sourced it. It's been open sourced for a while. It's at that location, so if you just search for it. The easiest way to find it is probably just go on Crates if you're a Rust person, Crates.io, and search for Delta kernel, and you'll find it, and that links to the docs and to the repo and everything. It's all there. We've worked pretty hard to make sure the docs are at least okay. They could probably be better, but they're not awful, and they'll get better. So hopefully the docs can also be helpful in explaining how things work if you're an integrator or want to start playing with it. There's example programs there that should show you if you're just a simple single-threaded kind of engine and you want to do it this way, here's how to use it. If you're a fancy multi-threaded engine, here's another way to do it, those kind of things. All right, so slight gear shift. I want to talk briefly about some of the challenges that we faced that I think are a little bit more interesting, and this is where also things might get a little bit more technical. So maybe, for the next 5 minutes, some of you will tune out, but then we'll bring it back, so it'll be okay. And maybe some of you will be more interested for the next 5 minutes, hopefully. The first one is not necessarily a Rust-specific challenge, hence the Rust in parens. Just got echoey. But the other two are sort of more Rust-specific. So this is a complicated diagram that you don't have to fully understand, but basically we just need to be able to split up the scan, like I mentioned. Part of reading a Delta table, right, is that you're gonna get a big list of files that you need to read. That's essentially it. Like, hey, here's a bunch of Parquet files that are included as what you need to do to read this table. And you don't want to just give those back monolithically, because as I said, you might want to farm them out. So basically, we support that the engine goes into the kernel goes away and processes the log, extracts some opaque metadata that it can give back to the engine. The engine doesn't have to understand that metadata. It just needs to hold on to it and keep it kind of attached with the file path. And then the engine can do whatever it wants to split those up. It can see, oh, I've got 15 files in this scan. I'm going to split those up to 15 threads, or oh, I'm going to spin up 6 workers and farm them out. And then it can send all of that data. That's the part that you can't see because it's under the closed captions there, but there's an arrow that goes over. And then wherever you are, in a thread or a node, or maybe just in the same thread, if you're just a single-threaded thing, you can read the parquet, come back into the kernel to do some final fix-ups via expressions, and then you have your final table data in whatever format you like, and you can continue your query processing whatever you are. So that's probably useful also for understanding exactly how DuckDB works, because this is sort of what they use. Okay, that was like level 1 of technical difficulty. Just checking my time. Oh, okay, I'm good. But how much I have? Yeah, okay, that's how much I have left. Good. The data passing one, this is an interesting thing. So in the Java world, which is the Java kernel was done first, it's pretty easy if you have some data and you want to hand it over to somebody else. You just give it to them, right? And you might hold on to it. You might not. They might hold on to it. They might not. Nobody cares, because later at some point the garbage collector is going to come along and fix it for you or clean it up for you once everybody's done with it. When you're in the native land, it's much more important, right? Like if the engine gives me some data and I hold on to it, but the engine doesn't know I'm doing that, and then they call free, I'm in big trouble. Likewise, if they give it to me and they expect me to call free and I don't, we're in trouble again, memory leak. So we wanted to find a way of making sure that the contract that we had with the engine was as simple as possible. And the contract that we wanted was, you can give me something for as long as a function call. And all you have to guarantee is that the data that you give me, as long as this function call lives, is good. And after that, you can do whatever you want. You can stack allocate this, call a function, and when you come back, your function returns, the stack gets cleaned up, all's good. And the way this works is, so you've read some data, and it's in a blob. We can ask you to extract on it. That's the name of the function call, and we'll give you a schema. And the schema kind of looks like it's the fully flattened out schema. So you only really care about the leaf nodes, right? So I might be asking you to extract like I should have probably used some different types here. This is less interesting, but it can be anything, right? It could be string, string, map, string, or whatever. These are like fairly simple types. And you're going to give me back an array or a slice in Rust terms of getters and a count of rows, which basically says, okay, for the life of this visit call, this is the callback, I promise that these getters have data in them that you can use. And the number of rows that you can get out of it is this. And this also allows columnar-oriented storages to give me back all of the data at once, right? Like we don't necessarily want to go row by row because you might have the whole column in memory. So it makes it fairly efficient to implement this for those kind of engines. And then the kernel can call back into these getters and just quickly read the data out. But all of this is only guaranteed to be as good for as long as the visit. And then once we get these primitive types out, if they're ints or something, then they're just copied. But if they're things like strings, they're borrowed in Rust terms, or they're not guaranteed to live for very long. So we'll make a copy of it if we need it. That sounds bad, except that we don't really need to do very much data. This is just little bits of metadata, so we don't end up actually copying very much. So that's the engine data passing API. This handles are the thing that we came up for making FFI as safe as we could. And the sort of problem we were trying to solve is, how do you pass opaque structs from Rust to C and back? So we're going down even one more level of complicatedness. This is the most complicated it's going to get. So if you don't really understand Rust and what an unsized type is, don't worry, there's only just a few slides. But the main things that we were trying to solve were ownership transfer. So Rust has a strong notion of, you own this, I own this, but C doesn't. So how do we indicate that? How do we deal with unsized types? So in Rust, if you have something that's unsized type, which is called a trait, When you make it a pointer out of it, it's called a fat pointer. It's actually like the trait, the pointer to the stuff and the V table for people who know what that means. You can't give that over to C safely because they don't have the same ABI for that. So how do we deal with that? Send and sync semantics in Rust were hard to enforce. And like we wanted these things from the C side to just look like pointers. We didn't want C people to have to think too much about Rust stuff. We wanted them to just get a pointer and use it. So the thing we came up with is called a handle. This is what it looks like in Rust. It really is just a pointer. But it says that the thing that you give back, this H that you're pointing to, has to implement something called a handle descriptor. And this repr transparent tells cbindgen, which is the guy who generates the C bindings, the header file that you're going to include as an engine. That tells it, hey, don't make it like a handle, just point inside the struct. Like the pointer is the thing that I really want you to expose to C. Lots of details elided here, but basically you can call just dot into, which is like the Rust idiom for converting types, to get a box into a handle or an arc into a handle. So this is kind of dealing with the shared versus mutable distinction. So you either have to have your thing boxed up, that means it lives on the heap, means you can pass it over, or you have to have it in an arc, which is an atomically reference counted pointer, and that lets you do sort of shared semantics. You can turn these into handles. I'm not even going to go through the slide, it's too much code. But basically, in your C code, what this ends up looking like is that you can get things and use things just as pointers through some type def. So in the H file, you see the handles get mentioned, and they're type def. But then in your actual engine code, you don't have to even worry about that, right? You can just say, hey, give me a pointer to this thing called shared extern engine, and then use it. And it all looks very transparent and nice. And is fairly safe. So on the Rust side, things are created correctly. You can only call these intos on the appropriate types. If it's unsized, we rebox it for you and make sure it's a thin pointer. If it's sized, we don't have to do this extra overhead. And it's very easy to go in and out of the handles correctly and not make mistakes. On the C side, you get just pointers. It looks nice. And the one piece that's, again, not fully safe is that we have to rely on the names that we give these types to indicate to C what we expect them to do. So here I had a shared extern engine. When it says shared, we mean that you can do whatever you want. Share it between threads, we don't care. We're gonna make sure like this is a safe to use as like a send and sync if you speak Rust. For things that should be only like mutual exclusively used, we put mute at the front. So you might have something called like a mute data or something, which means only one thread should ever have this. Like you own it, please don't share it. If you share it, things could blow up. We can't enforce that. They try to do it by naming. So where are we on the FFI? It works. It's in a separate crate as part of the kernel project. We also use this visitor model for doing schema and expression transfer. You can imagine that they need to be able to agree on these things. And we're developing it in conjunction with the community. We're talking to other connector developers, and right now in particular, we're working a lot with the DuckDB guys to make sure that we really are not making this be a second-class citizen. We want the FFI to be one of the primary ways that you can use the kernel. If you're a Rust system, use the Rust APIs. If you're a non-Rust system, use the C/C++ APIs. They're going to be equivalent. They're going to be both good. And with that, I'm going to invite Hannes to come up and talk a little bit about what they've done in DuckDB. Thanks.
Thank you. Wonderful timing.
Thanks.
Now we just have to solve the Beamer plugin problem while everybody's watching. It's the hardest problem in computer science. It's naming things, plugging Beamer. It's, yes. I've plugged it in. Perfect. Okay, hello everyone. It's wonderful to speak in what feels like a tiny room compared to this morning. So even though it's actually quite gigantic, I feel much more relaxed. So we're gonna have a bit of a, more intimate conversation about stuff. Now I just have to get the clicker to work. There we go. So I'm, as has been said this morning, I'm one of the people that works on DuckDB. And we've been working with the Databricks folks on the Delta kernel project. And I'm just gonna tell you a little bit like our side of the story. You just heard from Nick, like how they look at things. And I'm just gonna give you sort of the other side of the equation, because I think the Delta kernel project is really exciting from a sort of, how do we deal with new data formats in data processing systems perspective, right? Let me start a bit with DuckDB extensibility. So DuckDB is a data management system, but I think it's special in some ways from what we have seen before. And one of the things in which is different is that it's pretty highly customizable, right? You can write plugins, we call them extensions, for pretty much anything. So let me just go through the list here briefly. You can have an extension that provides a scalar function, like if you wanna, you have to parse some weird date format or something like that, you can make a scalar function that can live in an extension, and the scalar function is basically something that you load a shared object, it registers a bunch of functions, and then those are part of DuckDB and they can be used the same way. The same is true for aggregation functions. So let's say you're not happy with the 4 built-in aggregation functions that SQL usually offers and you want your own, you just add another one. I mean, just is a bit of an overstatement here. You add your own and you have to implement that, of course, it's on you. Window functions, like if you want, you can have your own window functions. But obviously, since we're talking about Delta here, Delta is a file format, and we call that the functions that can deal with random file formats, a so-called scan function. And why is it a scan function? Because DuckDB is interesting in that sense that we don't actually have to own data in order to treat it like a table, right? We can just run a query directly on a Parquet file, much like Spark does it actually. So traditionally, I think if you look at systems like Postgres or something like that, you will often find that in order to process a data set, you first have to ingest it. And this is not true for DuckDB. In DuckDB, we can run queries on almost anything, and as long as we have a scan function. There's lots of more stuff. For example, if you think you are better at query optimization than us, then you can write your own optimizer rules. Again, just some C code, and it's actually quite tricky, but some people do that. This morning, it was actually part of the keynote. Somebody did a demo, and I didn't even know they're going to show a demo. So I was almost dying when I saw the demo. But it worked out. You can actually plug a catalog, which means that, for example, we have this Unity catalog plugin now, which means that you can expose Unity catalog to DuckDB. Well, that is a plugin, an extension for DuckDB that exposes a new catalog, as the name says. You can also go much wilder. You can ship your own. You can have an extension that has its own parser if you want to do something crazy with SQL, and you can have file system and a bunch of other stuff. Like, we're essentially always expanding the amount of hooks in DuckDB because people come up with new and exciting use cases to hook. Right. Actually, before I continue about the technical things, I also want to talk briefly about organizational aspects. So DuckDB Labs is the company that employs most of the DuckDB contributors. And it's actually not funded by VC money, which is the standard way of funding companies these days, but we are working with other companies and providing services. And actually, in contracts with partners, and Databricks is actually one of those partners. So we've been working with Nick and his team on the Delta and Delta kernel and Delta Lake support for DuckDB. And this is really cool because the result of these projects become then available to all DuckDB users. Right? It's not like we do projects like with the CIA and then this extension for DuckDB never ever sees the light of day, but all these projects that we do, they allow partners to prioritize the features like Delta Lake support, but then in the end, they become available to everyone, so it's really cool. So the partners, in this case, Databricks, are really also giving back to the community, which is something we really like. Back to technology, easier. So here I have on this slide, I just want to show you how the scan functions really plug in into DuckDB query plans. So here on this slide, I have 2 query plans. And on the top here, okay, so in order to show the query plan in DuckDB, you have to say explain, like in Postgres. So here on the left, we have a query plan that reads, that does an aggregation on top of a Parquet file with a filter and a count. It's pretty simple, right? And you can see on the bottom here, when you say explain, it will show you the physical execution plan. And if you see this execution plan, it will say at the bottom, it will say read Parquet, and then you see a projection, and then at the end you see a group by operator. Pretty obvious, right? And it's important to understand that this will be executed as a streaming pipeline, right? So basically, it's not like we first read the entire Parquet file and then we sort of materialize in memory and reach it up. No, it's actually gonna read the data in these chunks, we call them chunks, and then put them into the group by, and then finally we produce output. And the Parquet extension in DuckDB provides this read Parquet function that you can see up there, and you can also see it again on the bottom left here, that there's now a read Parquet function in the query plan. And in exactly the same way on the right side, we see the same query, but this time it uses delta scan. And again, it's the same query plan, but in the bottom, it's just a different operator, in this case, the delta scan operator. So this is 2 examples for 2 extensions that provide scan functions, namely the Parquet reader and the delta. But what's important here is that while I spent half a year of my life or something like that implementing the Parquet reader for DuckDB, and now I don't have to do that anymore because somebody else is taking care of it. We didn't have to do this with delta scan support, right? Because of Delta kernel. And this is really a fundamental sort of departure. Like in the past, when somebody came up with a new file format, we kind of cursed the gods, right? Because it meant that we had to read the spec and deal with it and pray that it doesn't get more popular than, that it doesn't get popular despite, predictions, because that meant that we had to support it after all. There has been a bunch of sort of exasperated sort of screams about people using file formats wrong. And honestly, it's such a nightmare. Like, okay, this is a bit of a tangent and / rant. Parquet, building a Parquet reader is horrible because you're not only implementing the Parquet spec, you're also implementing compatibility with all the bugs that any system writing Parquet files has ever had in the past 20 years or so, right? So basically, you're like, oh, this was this bug in Hadoop. I'm sorry? Oh, you have implemented it. We can talk later. I feel you. But with Delta Lake, it was actually very different, as I said, because, yeah, we had Delta kernel. We didn't have to do that. Basically, Nick had done all the hard work for us. And we still, work with Databricks, which is weird. Anyways, you've seen this picture before. From our perspective, it's really interesting because, yeah, as I mentioned, we don't have to actually deal with the metadata format. And what's, I think, even more important here is also future evolutions of the metadata format, right? They adding a feature, we really don't have to deal with it. Delta kernel gets updated. As long as the engine APIs stay the same, we don't have to do anything. We just push the update button and then we're done. So this is really cool, and I want to walk you a little bit through how that actually works in DuckDB, because I think it's very elegant. So here is a schematic picture. It's a bit unfortunate that we cannot see the bottom here, but on the bottom is DuckDB, okay? Query comes in. Hang on. I am not above this. There we go. So on the bottom there is DuckDB. It gets a query. And then what happens is that, as I said, we have the extensibility for table functions, scan functions, so that it's implemented by the Delta extension. And what happens next is that this extension actually doesn't do a lot. It will actually just go to the Delta kernel via the FFI that Nick has described and tell the Delta kernel that we would like to read this path that the user has given us. We just hand that over. We're like, here, go look at this path for us. And then the Delta kernel will actually do its thing, fetch metadata, resolve predicates and all this kind of stuff. and then give us a list of Parquet files to read. Right? So from our perspective, we just use the Parquet reader that I've built at some point, and kind of jury rig it using the Delta kernel, because Delta kernel can give us a list of Parquet files to read. We plug it into our Parquet reader. It goes ahead and reads it in parallel, all the wonderful things. And then it will just look like a normal query result to us. There's some post-processing happening to deal with deletes, but I will spare you the details on that. What's also really interesting is that the metadata read will also go through APIs that we control, which means you get a consistent experience in terms of file access and general access to storage systems like S3. And how does this actually work? We saw this in the slide, like people type install Delta, but this is actually kind of cool because if somebody, this is something that's maybe not very well known. In DuckDB, you can basically type install Delta, and if the Wi-Fi would be working, you could do it right now. But what actually happens behind the scenes is that we will go to the internet. DuckDB will automatically go to the internet. We'll find out, what is your platform. In this case, it's ARM64 on OS X. It will look for a binary that's actually sitting there on the internet. So that's a shared object file, a binary code that contains Delta kernel as a static sort of linkage. And then we will download that, put it on your computer, check the signature, because we don't want to just do remote code execution by design. That seems like a terrible idea. But we check the signature, and then we put the file into your user folder, so you only have to do that once, and then we can read it. So that's really cool. Next, I want to briefly talk about Unity Catalog, which is a bit more experimental. I think this was something that came sort of in the last couple of weeks. And I've mentioned before that in DuckDB you have pluggable catalogs. And on the left, I have an example for the DuckDB SQLite extension, which is an extension that we have where you can let DuckDB read SQLite files. And fun fact, we can read SQLite files faster than SQLite because we can parallelize the query and they can't. So on the left, you see how that works. You can say basically attach file as, that's like a database name. It's a sort of namespace as user data 1 and type SQLite. You tell DuckDB, hey, this is going to be a SQLite file. Use the SQLite extension to read this thing. And then you can run a query. In this case, it's a query that just shows you the tables. Like from show all queries, select database schema name, and you can see that in that database file, there's a table, and we can then go ahead and just query it. And on the right, you see the same for Unity Catalog, where essentially we will install the extension. I told you about how that works. We have to create the credentials. And then again, we use the same pluggable API to just make these Unity Catalog tables look like tables in DuckDB. This is completely transparent to you. And when you start querying them, we'll instantiate the Delta Lake reader with the Delta kernel in it, and it's all completely transparent. So this is the thing that terrified me this morning when they showed it at the keynote, and I didn't know they were going to do it, but it works amazingly. So that's that. We're really happy about Delta kernel, and I have one more shameless plug I wanna sort of do in this talk. So I have 1 minute 30. So I've mentioned that we have all these extensions in DuckDB, and we have seen a lot of people making their own crazy extension. Like somebody made an extension so DuckDB could talk to SAP. That's just something people care about. Some people care about. And somebody made an extension for DuckDB to read blockchain files, which is like, okay, sure, if you want to do that. But so far, it's been pretty difficult to actually distribute these extensions to users. And we also had some issues with like, how can we deal with trust issues? We don't want to just basically do remote execution by design again. So how can we deal with user intent and so on and so forth? So from actually, this week onwards, you can essentially send us a pull request. And again, you cannot see this because of the translation, but I'm going to try to make this smaller. 1 second. So basically, you can send us a pull request with a YAML file that basically just points to a GitHub repository for a DuckDB extension. And then once this is merged into the DuckDB community extension repo, we will basically do the same thing like Homebrew and start building it. So basically, we build your extension for all the platforms. We are signed with a community key, and they're uploaded to our CDN, which means that all the people can download them. And then you can essentially, in DuckDB in the future, you will be able to install all these community extensions. And I think it's really interesting to see how far we can push this. And maybe DuckDB becomes the next sort of pip Python kind of environment where you just have a ton of an ecosystem essentially of extensions. So that's what we're really excited about. And that's what kind of it. Thank you.